So good afternoon, everybody. Welcome to our talk on MLD. Some of you might heard of this, some probably not, which is part of an overall problem landscape that we are going to develop. Just a quick intro. My name is Enno. Call myself an old school networking guy. Being involved with IPv6 since 1999. And I do a lot of protocol research and security research when it comes to network devices, lower level stuff. Next to me over there is Antonios, probably known to some of you as the author of the most powerful IPv6 security tool called Kron, and that's Jason. He's part of our team, and he actually did most of the research and most of the technical lab stuff. The agenda is quite simple. We have to first make you familiar with what MLD is, what it serves for, how it works, what are the main concepts and protocols and message exchanges involved. After that, we will lay out how we tackled it. The goal of this presentation is not just to describe a technical topic and a certain problem space related with that topic, but also to lay out how we go into protocol analysis. What are the typical steps? What are the typical tools? What you usually do, given we expect to some of you being this of interest for their own work. Obviously, the largest part will be covering results. What have you seen? What have you observed? What are the attack paths that we have identified? And there will be a conclusion on what does all this mean for the practical implementation of IPv6 networks, which probably all of you are going to face in the future. And some of you already have IPv6 in your networks. The background of this talk is, once you fire up Wireshark and look at the behavior of a typical, say, Windows system, which has IPv6 enabled by default, there is lots of messages looking like this, and Wireshark identifies them correctly as multicast listener discovery. This is a thing that hasn't been around in IPv4 networks. So once you first look at this, it's like you're wondering, what the hell is this? What's its role? Why is this there? And most notably, why is there such an amount of those messages? And they are part of pretty much everything most IPv6 stacks do. So you stumble across those messages. Next step might be like you try to find out, okay, what is this stuff? Is it specified? Is there RFCs? And the main RFC, or one of the core IPv6 RFCs, is 4861, describing neighbor discovery, which is the core mechanism for everything that happens within the local subnet, identifying neighbors, talking to the router. All this is done by ND, which in turn is specified in 4861. We can't save you from several RFC references throughout this talk. And in that RFC, there is a statement that goes like, joining the solicited multicast address is done using multicast listener discovery. And the interesting thing here is, there is a statement is done. And those of you familiar with RFC space will note this is quite untypical terminology for an RFC. RFCs usually either prescribe, that's the main point, behavior, then they have a normative character. And this normative character is expressed by terms like must and should in capitals. So the question is, does this mean it's prescribed to have MLD for ND? That core mechanism, or is it just has it the descriptive role here? Like, well, we know that it can be done, or it is this way, or does it have to be this way? This question will be quite important for this talk. And the third element leading to this talk is, I gave a keynote at an IPv6 security event 6 months ago, and there I cited as one of the structural problems of IPv6 the huge amount of complexity. And MLD is a complex element. So I gave that as an example Well, IPv6 is a complex thing in itself, and MLD is one leading example of this. So overall, it turns out the situation that we are facing when maybe getting into this, there is something which is ubiquitously there. We don't really know what it does, and if it has to be there, it's complex, and there hasn't been any security research on this thing so far, which we are changing today. So just a quick overview of what MLD does. MLD, DM stands for Multicast, group communication one-to-many. So usually there's a source communicating to many receivers. And to do so in an intra-domain setting, if there is multiple segment networks, the receivers of certain traffic have to signal to their routers, hey guys, I'm interested in receiving like the live stream of a Rapid Wien or whatever. They have to inform the routers, I need some traffic in order for the routers to communicate between amongst them. Oh, there's receivers in my network, please forward this multicast traffic in my direction. And this signaling actually is done by MLD, Multicast Listener Discovery, which exists in two versions. There has been a kind of predecessor in the IPv4 world, which was IGMP. And in MLD, there's the concept of queries and hosts. Those versions are both specified in different RFCs. The versions, the one thing about version 1 is, once a host like informs the router, I'm interested in receiving a certain channel, receiving certain multicast traffic, the router does not keep state as for this host, this specific host. It just keeps state like, oh, there is at least one who's interested in receiving that type of multicast traffic. This will become important later on. There's a second version, which is much more complex, which has a concept of source-specific multicast, which means you don't receive something just from any source, but just from specific sources. I want to get this type of information from that system and not from other systems. It is designed to be interoperable with MLD v1, so they, in a given network, both versions can exist in parallel. The exchange that these elements do are based on three main messages. There is a query, so a so-called querier, which is usually a router, can send out a packet like, anybody interested in multicast traffic, so please let me know, and let me know in which type of multicast traffic you are interested. And systems can respond to this by two messages, which are a report and a done. Before I tackle those in a second, there's one thing that should be noted. The queries are sent to a certain multicast group in itself, like, everybody here, just let me know as the router. And the answers, nodes actually replying, hey, I'm interested in a certain type of traffic. Those are sent to the multicast. Those are not sent, at least in MLD v1, to a specific device, but it's just like, hey, everybody, I let you know I'm interested in receiving certain traffic. And the second message type is a done, which actually means simply, I'm no longer interested. And like the router then has to take care, oh, I've not known that, I don't know how many there are, I just know there is at least one. So I have to take special precaution once anybody's leaving. I have to make sure there's somebody left. We will see this in a second in a certain type of packet. In MLD v2, the main difference as for these messages is that the messages are sent directly to the router, and there is no more done messages. Once a station wants to leave a receiving group, it signals this by sending kind of an empty report instead of I'm no longer interested. I'm interested in nothing, kind of. And as I already mentioned, there is a specific type of packet, the so-called last listener query. Once the router receives a message from a node, I'm leaving, it has to make sure, oh, has anybody left? So it sends out a special packet called last listener query, like a last round of drinks. Anybody still interested in something? Let me know. Oh, this was not a very smart move. Last thing, as for the technology space, is you need to know there's a technology called Mld Snooping, which is not based on routers, but on switches. And the switches can keep state like, oh, behind this port, actually, there's somebody sitting interested in the multicast group. So the switches can do selective forwarding, not just forwarding multicast traffic to all ports, but to just those ports which are specific to a certain multicast group. Within the specification, there are some, say, limits, some boundaries, some preconditions which have to be fulfilled by MLD packets. The specs say an MLD message must be sourced from the local link. It must be a local packet. So it has to have a hop limit of 1. It's not allowed kind of to traverse routers. And it has to contain a specific option, router alert, which means, hey, router, please take care of this specific packet. There is something in there you should know. The specs say messages that do not comply with these requirements must be dropped. The specs further say that once a node processes, or once a node receives a query, it has to process it as long as the query is received on any of the node's given interfaces. So actually it's allowed that a node gets like a one-to-one communication traffic instead of like a group call, which again will be important later on. Further, the specs say once there is more than one carrier in a given network, one device collecting information, who is part of a group, they have to decide who is actually the valid carrier, which they do based on their IP address. Lower IP address in a, say, bitwise or a numerical sense means I take over the carrier role, which is somewhat protocol design from the 90s, doing an election process based on an IP address, which can probably be modified by an attacker. That might not be the smartest move, as we have seen already in like Spanning Tree and HSRP. There is a number of broken protocols based on this type of assumption. And last, I think, okay. The next thing we have to keep in mind is the specification actually says once there is both MLDV1 and MLDV2 in the network, they kind of fall back to MLDV1 as they all have to support this, which then again is a kind of 90s approach, which allows what we called at the time forced dialect downgrade. Two versions of a protocol, one is say better or more evolved than another one, and we can easily force everybody to use the older one by just simply sending packets. Keep all these things in mind now that we look at the actual reality of implementation and that we then look at potential flaws in the actual reality.
Okay, let's discuss some facts or supposed to be facts and see if they turn to be myths in the end. First of all, the neighbor discovery protocol is a core protocol in IPv6. It is needed in order IPv6 to operate. It is mainly used for translating IPv6 addresses to MAC addresses and vice versa, something like the ARP protocol, but makes more than this. The point is that, as we saw at the RFCC, it is written that joining the solicited node multicast address is done using MLD. The solicited node multicast address is an address which is used by the ND process, this core functionality of IPv6. So it is implied, finally, that in order to operate IPv6, you need MLD. Another fact is that MLD, in most operating systems, cannot be disabled. If you want just to disable MLD, you cannot, at least in most of them. Now, regarding Windows, there is a way to disable MLD, but if you do so, the ND process simply breaks, so you don't have IPv6 at the end. So up to now, it sounds that, okay, it seems that we need MLD for our IPv6 functionality. However, if you try a small test, and if you use your host firewall in your system, either Windows or Linux or FreeBSD, and you block outgoing MLD reports, and you also block incoming MLD queries, you will find out that the NT process still works. So even if you cannot disable it, even if you think that in the RFC it is implied that you need MLD for ND, finally, if you block these messages, it still works. And moreover, in OpenBSD, although MLD is not enabled by default, the ND process also works. Now, let's think about it. The ND process takes place using this weird solicited node multicast address. Okay. The name shows that this is a multicast address, so it is a multicast functionality. However, the local link multicast is actually broadcast. It is broadcasted. There is only one way to enforce real multicasting in the local network. This is to use Mld Snooping. So you may think that, okay, this is where I'm going to need MLD. I'm going to enable Mld Snooping, so MLD will take care of this solicited node multicast addresses, so we have a case. Well, it turns out to be that in the reality, in the real world, some vendors like Cisco, for example, at least as far as solicited node multicast addresses are concerned, they simply broadcast them, even if you enable Mld Snooping. So in the end, this kind of addresses are broadcasted everywhere. So what's the reason for multicasting? Or what's the reason for MLD, at least as far as neighbor discovery is concerned? MLD is pre-enabled in Windows, in Linux, and FreeBSD systems. And if you notice the booting process of such an operating system, you will find out that the first packets sent by such a system during booting are MLD packets. Even before obtaining a link local IPv6 address, even before obtaining a global unicast IPv6 address, as we call it in IPv6, the first packets are sent by these systems are MLD reports. To make matters worse is the fact that each of these messages are sent more than once, because according to the RFC, we must be sure that the reports are received by the routers. Now, another observation is that most of these operating systems join different groups. Of course, all of them join the corresponding solicited node multicast address group that they belong to. Some of them join it just once, because they have just one IPv6 address. The Windows, for instance, join twice, because they have at least two IPv6 addresses. However, they also join some other addresses. Windows joined this weird, let's say, FF02::1:3, as well as the FF02::C, which is used for SSDP, a kind of proprietary protocol for Windows. While on the other hand, FreeBSD joins a group which implements the so-called node information query specification. This is an experimental RFC. This experimental RFC has been defined in order hosts to be able to try to operate in a DNS way, but without using DNS. To get host names, to get fully qualified names, but without having to use DNS. But this experimental RFC, and surprisingly enough, at least for us, we found out that FreeBSD joins the group that belongs to this experimental RFC. So we can very easily say that, okay, it's quite easy if you sit back and watch the traffic in your network to find out which operating systems do you have. Now, a more specific case. Normally, all these messages, MLD messages, are sent to multicast addresses at the local link. However, in the RFCs, it is defined that you can also use global unicast addresses. And we found out that this is really the case with the exception of FreeBSD. And why is this important? Because this allows you to interact in one-by-one with all your clients in your network. You can avoid informing all your participating nodes for a message. And this is quite convenient from the attacker's perspective. Okay, we saw that MLD actually in the end is not that important, at least for the basic, for the core IPv6 functionality. So, what's the big deal of having it anyway? Well, MLD is a complex protocol, especially the version 2. And when something is complex, it allows you to break stuff. Up to now, there have been published at least 6 CVEs related with several vendors, which have been resulted to DOS conditions and even to remote code execution. So if you want to do some study about yet another protocol in the end, what you should do? Okay, we read the specs, we take our lessons, we build a lab, we create a test plan, we will see it in a minute, and then we just have fun. Okay, but what we should look for in such a protocol like MLD? First of all, implementation problems. Do all vendors implement this protocol in the proper way? Are there any problems regarding parsing, which means fuzzing? Moreover, are there any RFC compliance issues? Do they respect RFCs? And if you think that, okay, this is lame, it's not that important, well, it turns out that in some cases you can put on your findings and exploit this RFC non-compliance issue in order to use it for more malicious security purposes. And finally, we were also interested in finding designing flaws and unwanted or unexpected protocol behavior. This means how to break MLD.
Can you hear me? Oh, good. Okay. So now I wanted to test like how to break MLD, what to do with it, and if it's not that important, okay, we wanted to like have a look at how does it affect the security posture of a normal enterprise environment. So we built our lab. We used Cisco switches and Cisco routers for it, and several VMs. We use Windows, FreeBSD, OpenBSD, and several flavors of Linux, CentOS and Fedora, and so on. For the Cisco switches, we used the latest version of the iOS for the Cisco we had at hand, which was 2960. And for the router, we also used the latest version of iOS, which was, in our case, 15.2, 15.4. So we started like having a look. Okay, we now kind of know at what we want to have a look at, but which tools are there available for testing like what we want to test? First is Chiron, Antonio's tool. There are also several tools, but they are kind of limited in what they can do regarding MLD. And then there's also, okay, so what are we going to fuzz this protocol with? And we decided to use Dizzy. Dizzy is a really practical fuzzing tool, which was developed by a guy at ERNW at the company Eno leads and I work at. And with that in mind, we just set ourselves like, okay, let's have a look how we can interact with Chiron, with the protocols and the nodes, and how we can use Dizzy to build packets and define packets and send them really fast and so on. So I'm going to show you a Dizzy script and how it looks and how you can define packets in a while. So now we're going to have a look at some results and what you can do and some impact which having MLD in your network, which all of you do if you run IPv6, can have to the routers, to the switch, to the infrastructure in general, to stability. First, when you start to look at the code base, the kernel in Linux systems, until the latest version, which was, I guess, committed to GitHub in August, I'm not sure, they accept messages with a hop limit bigger than 1. So you have this situation where MLD messages have a hop limit restricted to 1, so they cannot be routed, but Linux systems, until a couple of months ago, accepted them, even if the hop limit was bigger. So that's a small problem. It's not that a big deal, but it sets the tone for what you're going to find. There's also the case that a lot of Linux distributions accept MLD messages without router alert option. They are invalid. The router is not going to look at them if he doesn't know that he somehow should look at them, because there's some interesting information there. And there are some other compliance issues, like CentOS accepting MLD messages when the source address is a link local multicast address. That shouldn't be the case. That's even prohibited in the IEEE specification of Ethernet. It says no multicast MAC address should be defined as source addresses. So you see there's a lot of stuff going on here. We further had a look at how Windows behaves, and we found out, okay, when you send certain types of packets to Windows, Windows replies with its global unicast address, which shouldn't be the case. All MLD messages should come from link local addresses, not from global unicast ones. Going further, when an Mld report is received by any node in a network, it should come from a source address which is a link local one. It should be checked, it should be tested, and if not, it should be dropped. In MLD version 2, it is strictly prohibited. In MLD version 1, it's not explicitly said. So it sets the tone for what we're looking at. It's really ugly and it's really complex, and no one knows how to implement this, particularly because there are a lot of small details which are missing. As Eno and Antonio have already mentioned, we can interact with all nodes in a one-to-one manner without relying on the functionality of the protocol, which is talking to everyone. You further find that there are funny things like virtualized Windows hosts behaving like this. I mean, totally unresponsive and only with MLD version 1 queries. When you send a lot of MLD version 1 queries to Windows virtualized hosts, they just start behaving this way. When you send MLD version 1.2 queries, they just behave normally. I mean, if, we didn't put the screenshot here from Linux systems or FreeBSD systems, CPU load reaches 2%. So this is not normal behavior. And this happens in several virtualization platforms. So there's something running under the hood. And the code is apparently different because MLD version 1 and MLD version 2 are not handled at least in the same way. They shouldn't be, but the difference shouldn't be that big. And there's also the fact that once you have an MLD in your router, and once you enable, for example, PIM routing, the router starts learning, okay, which hosts want to receive traffic to which multicast groups. And the question is, okay, what if I tell the router there are 100 or 200 or 300 or 1 million listeners which are interested in 1 million groups? And what you reach is that, for example, in our case with our Cisco device, after 6 million joins, which is the default configuration, you can join 6 million groups. Yeah, the device stops responding, the console stops working, and it flickers. Sometimes it works, sometimes it doesn't. And we're going to actually show you how you can, at the time you start sending MLD queries flooding the net with MLD queries, you start seeing like the CPU overload of the Cisco device peak. So
we will quickly demo this.
We will have a look at this. So I'm going to join. Okay, so how do you look at the groups which our router has joined? It's just show IPv6 MLD groups. And you see there's only one group, FF08 cool, and the other one is because for DHCP. Then I have a dizzy script here, a fuzzing script, which I wrote for the tool, which this guy IRW wrote. And I start sending packets. And you can see here, it starts filling up. Okay, it's not that bad. Perhaps the device it's really robust. But then when you start having a look at the processes and what what they are consuming. Like, you start seeing that it's not, you can't ignore this if you're a network administrator and you have this running in your network. Like, a person, any host, because MLD functionality in Windows and Linux is not a privileged one, can start sending MLD queries and overload your infrastructure in this way. We also have had crashes, not crashes, but situations where the process of SSH, for example, was actually failing at allocating memory. So there's certainly something going on in here. That's for the short demo, just so you get a feeling. Okay, and then, yeah, so you can flood the network, you can use MLD in order to impact the infrastructure, so you should have a look at it, at least consider when you're developing countermeasures or securing your network. You might think, okay, the devices these guys brought with them aren't that high-end, they're middle kind of devices, like for middle enterprises, but we also tried with an ISR, which is a Cisco device which is particularly developed for big enterprises, and we also saw the same result. We encourage you to do tests in your network, to download DZ and to try some DZ scripts which will be made available. And this goes on and on and on. For example, in Windows, you get, for every query, you get 8 packets. So if you have 200 hosts, you get 1,600 packets, and you can scale this. As you've seen, there's no network infrastructure which is going to withstand this kind of flooding. If you get this amplification factor, it's really going to impact your network. It's not something a sysadmin or a network administrator can ignore. As you can see in this image, the red line is the queries we sent with a couple of hosts, 4 or 5 hosts. And the green line and blue lines are the reports which were actually sent. So Cisco and the way the Cisco devices behave make it possible for people, by means of using MLD, to really not abuse, but kind of impact the overall stability of your infrastructure. So now we're going to show you like the real interesting demo from the perspective of how MLD works and how it is, what is it made for. This is a typical scenario where you would have multicast, apart from neighbor discovery. You have a sender, you have MLD, because it's IPv6. You have a receiver, you have MLD, because the receiver is interested in some traffic. And you have interdomain routing, PIM, between the routers. So, and you have the attacker, which wants to prevent hosts in its network from receiving this kind of traffic. So how would we go about preventing the receiver from receiving the traffic he's interested in? We can take over the courier role and then lie to the network. Hey, there's no guy interested in this kind of multicast traffic. We can also first lie and take over the courier role, and we don't send any more queries. Or we can fake this last listener call, which Enno explained as the last drink call. And since we can fake it, some devices, we become the query role, we fake this listener query after we lie and say there's no one interested, and devices start behaving oddly. And for example, in that way, you can remove a group from the router and prevent devices from actually receiving traffic they're interested in. There are several attack vectors, but we're not going to discuss them because we would have to go in depth. Just so you know, there are several variations of this: becoming the querier, then lying about interest, and then sending the last querier call, and so on. And there are problems in the implementations. For example, Cisco switches, the one we have here, doesn't forward last listener calls. That means it's even easier because you can lie to the network. There's no one interested in this kind of traffic, and then the Cisco doesn't forward the actual last listener call, which comes from the router. Hey guys, is there anyone still interested? The Cisco switch doesn't forward it. So it becomes easier if you want to attack it. And there's a hype going on about multicast. There's people who want to implement things based on multicast in smartphones, in every single device. IPv6 is in a, IPTV is in a boom. And if you want to implement video conferencing based on multicast in your network, well, you'll see how it can go. Like, we're going to show you a real shareholders meeting and how it can go. Okay. So here we have a here we have a virtual machine, and we have two virtual machines, Ubuntu 1 and Ubuntu 2. Here we have a transmitter. We are streaming a video of a shareholders meeting, and then another virtual machine, which is receiving the video, is receiving it over interdomain multicast routing. So this application told the network, hey, I'm interested in this kind of traffic going to this group. The sender is just sending it to the network, it's being routed, and it's reaching this device. As you can see here, we have two routers and a switch. They're separated through VLANs. We won't go into much detail about the setup, but this is like the scenario. You have a sender, a receiver, and you have some content which is being broadcast, multicasted. It's not working. I'm not sure why it stopped working in the middle. Let me have a look at this.
I mean, that's always a risk with live demos. Still prefer to do, we don't do recorded demos, so you have, I mean, that's just real live networking. And actually, MLD in itself, to some sense, this is a bit like, I wouldn't say a typical MLD scenario, but with MLD you have in real life quite a number of like inconsistencies, devices behaving in one way or another way and not doing what they are expected to do. Well.
Yep.
That's it.
Oh, actually, you're right. The DZ script was running, and
yeah, we can still take the quick question until you.
Do you see these vulnerabilities you're seeing with V6, with IPv6, also with IPv4? Because MLD version 1 should be almost the same IP version 4. So I expect the Cisco router to also be vulnerable to denial of service attacks on IPv4.
Actually, we never tested that one. One of the main points of this is there is a counterpart to MLD in IPv4 that is IGMP, either version 2 or version 3, but those are not necessarily enabled by default, and those are not needed for like the core functionality. ARP doesn't need IGMP. In IPv6, you don't really know does ND require MLD or not, but the fact is all stacks come with it pre-enabled, and so you just have it without maybe being even aware there is some complex protocol sitting in the background and being exploitable in several ways.
Second question for the Mld Works. RFC 4890 defines firewall recommendations for IPv6, mainly ICMP stuff.
Yeah. Actually, it doesn't. 4890 says on the local link you should pass MLD.
On the
Local link on transit, but on transit it's not supported. It's not supposed to be transported anyway, given the hop limit. MLD shouldn't pass transit points anyway, so it's in the RFC 4890. It's in the section of is going to drop anyway. But for the local, they explicitly have it with a permit statement. If you transform 4890 to an ACL.
Yes, on the other hand, if the hop limit is already reached 1 and the router is buggy, your immediate default gateway to the internet is buggy and has forwarded these MLD stuff, you're still vulnerable if you don't filter at the gateway. So okay.
Which brings us to one of the actual recommendations later on. Filter MLD, both on transit points and as I will state later on, filter it on the switch infrastructure level. Actually, I will for the moment until this is maybe resolved. If it's not, we can show it later on once the official track is ended. So it doesn't get resolved.
I'm working on it. The router just
we probably run out of time. Yeah, which is quite unfortunate. The demo would have been. I mean, you saw this. There was a video stream. It wasn't received. It should have been received. And then what actually happens would have been like on a local network. We tell the router, hey, give us the query role. We actually sent a spoof packet. Nobody's interested anymore in receiving this traffic, and then actually it's stopped that the traffic gets forwarded, and everybody who legitimately wants to receive traffic doesn't get it any longer, which of course in an enterprise environment would cause all types of like compliance and finance issues. The problem is we don't have time.
Yeah, but I'm just going to interrupt it really fast, like just so they can
let's try this. I mean, actually, the key takeaway as for the recommendations later on in like 3 minutes will be filter it wherever you can. If you can't really, if you're not sure that you need it, but filter it on a switch port level with a port echo. There is no MLD guard. Filter it on transit. That's the main recommendation. So I can very quickly skip this later on.
Problem. And
We've run out of time. Thank you for this interesting thing. And
hail to the demo gods. If you still have questions, I'm afraid we can't take them now. You guys will still be around.
Yes.
So take the opportunity and catch them outside, asking questions. We'll continue with IPv6 here. And some cloud topics in the other.
May I add one key takeaway in one sentence. There's the complex protocol you probably don't need, which can cause harm. Filter it, and get aware of what is happening in your IPv6 network. Thanks for listening.